Welcome to our NPTEL lectures on the DC microgrid and control. We shall discuss today about the modeling of the converter, that is very important topic till now we have discussed. Modeling of the converter in the microgrid power system. So, we will have both the converter required to be designed, that is actually AC to DC as well as DC to AC. In the next subsequent class we shall do that DC to DC also. So, we shall discuss about this will be our presentation layout today, power converter in microgrids, modeling of voltage source PWM rectifier, followed by the control of the DC link voltage, single phase AC DC inverter with 2 switches, and modeling of single phase voltage control voltage source inverter. These all we will see together. As we know that with the progress of the using electrical energy in industry, transportation, commercial and residential application, there come the need to convert this energy for an appropriate voltage level. For example, we generate the generator around thousands of around 1000 to 11 kV voltages, and it has been transmitted based on the transmission line level. And for this reason, and thereafter what happened, you are rectifying it and you are running a different kind of converter. If you have a local railway locomotive, then you require to rectify from the 11 kVA line. So, for this reason you may have from AC to DC or from high voltage to the low voltage and so on. Similarly, we may have adjustable speed drive, since we have a constant frequency supply and drives are most of the cases at constant frequency, runs at the constant speed. For this reason, inverter converts direct current or DC power generated by the DC into the sinusoidal alternating current, and it should be it should be required to be sometime required to be a variable power. The photovoltaic cells PVs are the different kind of DC sources, since it required to be connected to the grid or battery, it required to be, or UPS, it required to be converted into DC to AC apart from adjustable speed drive. The high speed micro turbine generator are the source of high frequency AC power, because these generators are designed for the high speed operation. They are lightweight and low volume, since you know that essentially V is proportional to, or if you write proportional to F, more the frequency. This other part that is basically comes under the picture is a B and N can be reduced. Mainly A is the area, B is the flux density, that depends on the material, and A is in a number of turn. So, A and N can be reduced by increasing the value of F. So, they use natural gas altogether with their fuel cells are considered to be the green energy source, because they have a minimal carbon footprint. So, that can be used for many microhydral or fuel cell based generation system. Apart from that, we have a variable wind speed generator, have the same operating principle as that of the micro turbine, except they run at a variable speed and generate variable frequency AC power as well as voltage. So, for this reason we require to have a processed energy, and this process has been done by the different type of AC to DC or DC to AC type of converter, power converters in microgrids. To utilize the variable frequency AC power sources, the generator power is rectified to the DC power using a AC to DC rectifier, that is a simple rectifier, and thereafter DC to AC inverter are also used to convert the generator DC power to the AC power at a system operating frequency as illustrated in the system. So, you have a wind turbine or the variable speed permanent magnet motor generator, and then it will be converted to the AC to DC, and here you require to track also maximum power point. So, for this reason you have a buck boost converter that will help you to actually track the maximum power from this wind or hydel setup. Mostly it is wind setup. Thereafter you may have community storage for the local usage, also controlling the peak power management. Thereafter it can be converted into the DC to AC and required to be connected to the grid to send it to the, and this is for the microgrid. This is you may have a local load and you can send to the local utility, or you can dispatch power to the active converter. Now, principle of modeling, that is something we require to investigate time on it. Modeling of voltage source PWM rectifier. The voltage source rectifier is widely used for this purpose, because please understand why we require this active rectifier. We may use in case of also 400 converter converting AC to DC with a unity power factor, also having a low distortion into the and all the power quality issues into the AC side. So, it is one of the main part. Instead of the diode bridge rectifier, we will use this PWM rectifier. Another issue is actually the power rating of the diode. So, once high current flows through the diode, then if it is and this power diode will drop around 1 volt. So, in that case this drop is quite huge, and sometime to negate those drop also we use synchronous rectifier, that is MOSFET based, that is generally used for the low power application. But for the high power application we require control rectifier, and we require different kind of power quality issues, and for this reason PWM rectifier is preferred. A PWM rectifier shown in the figure 2 draws near sinusoidal current from the AC mains. Otherwise, you know that if it is 3 phase 3 wire system, if you fit to the diode bridge rectifier, current will be like this for the RL kind of load, and for the RC kind of load, and it is quite bad, this will be the thing for RL, and this is for the RC for diode bridge rectifier. And you do not want that, you want a sinusoidal voltage, and for this reason we require to incorporate this PWM rectifier. The DC output voltage can be regulated, and the input power factor is just, thus it can be adjusted. So, you can control the PQ control, that will come little later, can be done through the PWM rectifier. The converter consists of a 3 phase bridge, a high capacitor, so that actually voltage ripple in the output side is low, high capacitance of the DC side, and the 3 phase inductor in the line side. This is called line inductor. Ultimately, this is a boost topology. This LS help us, mostly it is required to be the source inductance. If source inductance is not so high, then you have to add the external inductance. The voltage at the midpoint of the leg of the pole voltage V1 is a pulse width modulation PWM nature. This voltage consists of the fundamental component of the line frequencies beside the harmonic component around the switching frequency of the converter. So, this will have a problem of the voltage THD to be higher, but since it has an inbuilt low pass filter, so current THD will be lower. At high frequencies, this harmonic component will be filtered out by this line inductor LS. Hence, inductor current is nearly sinusoidal, the fundamental component of Vi controls the flow of the real and the reactive power. The phasor diagram of VSR I will come little later under different operating condition is shown in next figure, that is figure 3, and it is known that the active power flow from the leading voltage to the lagging voltage and the reactive power flow from higher voltage to the lower voltage. So, please understand that this is one of the important chunk of its operation, that the active power flow from leading voltage to the lagging voltage. So, you can control the flow of the active power by controlling the power factor, and the reactive power flows from the higher voltage to the lower voltage. So, this principle will be applied to actively control the P and Q. Thus, both the active and the reactive power can be controlled by controlling the phase. If you control phase, then you can control the active power, and if you control the voltage level, you can control the reactive power, and the magnitude of the converter voltage fundamental component with respect to the grid voltage. You see that this is the reference. So, this is the reference. A shows that phasor diagram of the voltage source rectifier under different operating modes, that is unity power factor, where voltage and current are at a unity power factor, and this one is VIF, and in B it is lagging power factor. So, you have this value of the induction and this current is lagging. Similarly, here in C current is leading, you got a leading power factor, and it is regeneration, you feed the current and voltage will be 180 degree phase shifted. So, power will come back from the DC side to AC side, and it will act as a inverter. In this figure, subscript F shows that fundamental component. So, IF is a input fundamental components. So, figure 3 illustrates the operation at the unity power factor as I described, and others are lagging, leading and the regenerative way of operation. Figure 3b, plus recall this figure 3b, this one shows the lagging power factor operation. The real power flow from AC to the DC side, since Vs is greater than Vi, the reactive power flows from the mains to the converter side. So, this is the mode of operations in case of the lagging power factor. Similarly, in 3C, the leading power factor, the real power flow from AC to DC same, while the reactive power flow from the converter to the grid. And just reverse happened in case of the 3D, that is the regenerative mode of operation, shows the operation under regeneration mode with the real power flow from the DC to the AC side at unity power factor. Figure 2 shows that figure 2 we have seen that actually VSR fed from the AC mains, the RMS value of the phase to the neutral voltage to the main AC supply can be defined as these three are unity power factor and 120 degree phase shifted balance 3 phase load. Now, we shall continue to model this thing in stationary reference frame in alpha beta frame. So, the 3 phase voltage can be transformed into 2 phase electrical quantities, that is called stationary alpha beta frame, V alpha and V beta, which are the component of the voltage vector Vs along alpha axis and the beta axis, and described by the equation 2, that is V alpha equal to 3 by 2 Vs1 equal to root 3 by 2 Vs cos omega t. Same way Vs beta equal to root 3 by 2 Vs2 minus Vs3 equal to 3 by 2 root 2 Vs sin omega t. This voltage can further be transformed into a synchronously revolving dq reference frame, where dq axis is aligned with the voltage vector Vs and d axis lags the q axis by 90 degree as shown in the figure 4. So, this is the representations or transformation to the alpha beta to ABC to the alpha beta frame. It is not a very difficult thing. You have studied that resolution force in class 12, that is actually 3 forces are 120 degree apart. They are made to the they are been put into the x and y axis. So, x axis is alpha axis and y axis is the beta axis. Same transformation is been used here, as simple as that. So, q now we shall, once we rotate this alpha beta frame into a synchronous speed, then it becomes dq, and thus what happened at this stage, this electrical signals which was in stationary, and since you were stationary you look like that it is rotating at 50 hertz. Once you rotate at a synchronous speed, those entities are remain stationary with respect to you. So, transforming alpha beta to dq frame, so SQ can be written as minus Vs alpha sin theta plus Vs beta cos theta, and St equal to Vs sin alpha sin theta plus Vs beta cos theta, where theta is the angle of the d axis measured from the alpha axis. So, this is the when it is rotated at a sync frame, and this is the initial reference, with that we may have angle theta. So, this becomes d, and perpendicular to it, it should be q, and ultimately this will become St, and perpendicular, this is the basically S, you will have it has been split to Sd and Sq into components. Now, similarly, so we can write the voltage equations of the VSR in the dq reference frame are being represented here, where Rs and Ls are the inducted resistance of the source inductance and the source resistance we can talk about. Now, microgrid has a problem, you know that actually predominantly it is resistive. Generally in case of the normal grid, we generally neglect the value of the resistance and it is predominantly inductive, but we shall take care of these things in later stage. So, Vst equal to, then it can be represented by Rs Ist plus Ls Isdt. Please understand, I was telling it looks like DC, but it is not DC. For this reason this term will survive, and similarly omega Ls into Iq, omega Ls Isq plus Vid. Similarly, you got Vsq Rs Isq plus Ls dq dt minus omega Ls Isd. These are the cross term. Here with Isd you will get this Isq, and here with Vsq you will get Isd plus Vid, where omega d is a grid frequency radian per second and Vid and Viq. So, Viq are the converters sites voltages. Control of the decelerating voltage, it is quite the important aspect of controlling the active rectifier or PWM rectifier. Control of the decelerating voltage require a feedback loop. The DC voltage Vd is compared with the reference Vrf, and the error signal E obtained from the comparison used to generate the template waveform. The template should be a sinusoidal waveform with the same frequency of the main supply. So, we have to generate the unit template from the voltage sensor. Now, look, This is the voltage supply, thereafter is Is, you have a source inductance, generally you have to put extra source inductance, you generally require this value of Ls to be 0.05 per unit. Accordingly, you can, and generally if it is voltage is quite higher, then you may require to use the multi-level converter. I was, for sake of simplicity, we are linking 2 level converter. Now ultimately you got a VDC and that has to be compared with the VREF, and you got an error signal. This error signal will multiply, will be fed into the PI controller, then whatever reference will come out, it will be multiplied by the unit voltage template, then the reference for this converter will be generated. This template is used to produce the PWM pattern and allows the controlling of the rectifier in 2 different ways. One is the voltage source current control PWM rectifier, for this is size of the inductor required to be higher, and the voltage source voltage control PWM rectifier. And in first method we shall see that this is quite familiar. The first method controls the input current and the second controls the magnitude and the phase of voltages of VMOD. It is abbreviation, magnitude and the phase of the voltages. The current control method is simpler and more stable than the voltage control method, and it is inherently protected from the short circuit. Now let us come to the AC to we have talked about AC to DC converter, that is rectifier. Now we will talk about DC to AC inverter. You may find that its application in PV array. You have a DC and you have to connect a local AC grid, and for this reason you require to rectifier. In IIT Roorkee we have a DC microgrid, we have AC microgrid, we have DC microgrid test bench, and we have genuine AC microgrid because ABB has donated that battery setup, and so we have a solar power installation at the rooftop, and excess power is being sent to the battery to store, and ultimately you have AC to DC converter, then bidirectional AC to DC converter, then you have a battery charging, that is also bidirectional AC to DC converter. So you have a whole system in our campus. So inverters, let us come to our studies. Inverters are used to convert power from DC to AC at the system frequency in the integration of the renewable energy, mostly solar because it is DC, into the power grid. It is can be shown in figure 6, depicts the single phase converter with 2 switches for simplified discussion. This single phase inverter is usually used for the low power application. Mostly you have a rooftop system of less than 5-6 kilowatt, then we can go for this kind of topologies. The PWM technique is used to achieve an AC voltage of the fundamental frequency of 50 or 60 hertz depending on the what kind of country you live in, and if the switch S1 is on, the potential at a point A is same as that of the positive DC bus, and if the switch SW1 is on, the potential of the anode A is that of the negative DC bus, because first this switch is on. So, this point will go to here, if this switch is on it will go to the lower DC bus. So, principal operation, you can have a different kind of PWM technique, you can have a bidirectional PWM controller, you can have a unipolar bipolar PWM controller, you can have a unipolar PWM controller. Here it is a unipolar PWM controller. For this you can find that it is switching to plus VDC to minus VDC. Figure 7 show 2 waves are compared, the sine wave Vc that is designated as a control voltage and a triangular wave Vt with amplitude and the frequency higher than the sine wave. So, this is the, so you have a modulation index. Please refer your PWM technique in your books or my previous NPTEL Tech lectures in advanced power electronics. So, control voltage and the triangular wave Vt, the amplitude and the frequency higher than the sine wave. The sampling rate is Ts equal to 1 by Sf, where Fs is the frequency of the triangular wave. The switching policy based on the comparing Vt with Vc, this is the principle of the bipolar PWM. So, once Vc is greater than Vt, SW1 is on and SW1 equal off. So, you got plus Vdc. Otherwise, if Vc is more than Vt, then switch SW1 is on, minus is on, and ultimately you get negative DC bias voltage. If it is coupled to the 0 voltage, you get 0 voltage. Now, the magnitude of the fundamental of the AC output voltage is directly proportional to the ratio of the peaks of Vc and Vt, and this ratio is defined as the modulation index. So, modulation index Ma is essentially the ratio of Vc max by that carrier wave or a triangular wave. The peak of the fundamental component of the voltage is Van1 equal to IDC by 2 into Ma. The instantaneous value of this output voltage will be given by In1 equal to Vdc by 2, Vdc by 2 Ma sin fundamental omega t and the harmonics, where omega e is 2 pi into Fe is the frequency of the sine wave in radian per second. Now, we can come to the modeling. The single phase voltage control VSI with a second order LC filter, because you got a, because you generate PWM and that is not allowed to connect, and ultimately there is a limitation of the voltage TSD and the current TSD is been imposed. For this reason, we require to have a filter for grid connected inverter. Also, if it is a single phase load, that also required to fit with the filter to make this current sinusoidal. So, VSI with the second order LC output voltage is shown in figure 8. Voltage and the current equations of the single phase voltage control are definitely, it is given by INV equal to RF into IL LF didt into VA, that is the terminal voltage at this point or the load or the grid, and the current will be given by IL plus I0 minus C dV dt. The voltage and the current equation from the single phase voltage control VSI in dq axis, we can make it a transformation. So, inverter D will be given by RF ID LF dq dt minus omega LF IQ plus VD. Similarly, for the Q domain, to RF IQ LF diq dt to omega LF ID plus VQ, and similarly this current will be transformed to this method ID and IQ. Thus, you can control the flow of current of ID and IQ depending on the requirement. So, where please understand that inverter, that is essentially that depends on the modulation index, that value will be K into VDC is the output voltage of the inverter, and since it is switching on 1 to 0. So, it can be 1, 0 or minus 1 depending on its pole voltage which has been clamped to, is a control variable depending on the state of the switches in the single phase full bridge converter is been controlled in case of the VSI. VL is a current through the filter inductor LF, and RF is the resistance of the filter inductor, and CF is of course the filter inductor for the capacitor. I0 is essentially the load current, that is given by VA by Z. Z is the load impedance, and omega is the angular frequency, fundamental angular frequency. Now, we have to control this control loop. An AC voltage controller with cross coupling, because you can see that omega terms comes, omega LF comes with the cross coupling. This term is essentially cross coupling, this term. Here it is IQ and here it is ID. That is what I am saying. So, that an AC voltage controller with the cross coupling filter, cross coupling of filter CF, and the inner current controller with the cross coupling with the LF as shown in the figure. So, it is Vref minus Vd equal, that is fed to the Pi, and thus you generate this ID reference. Similarly, what happened, there is another loop, please come into the picture, Vd, thereafter you got a Vq, Vq will be multiplied by Cf into omega and it will be substituted, and similarly Vq will be subtracted from the Vref fed to the Pi, and this term Vq will be multiplied with the Cf. This is the inner current loop. Similarly, once you start with the inner current loop, you start with the Vd and Vd ref, Vq and Vq ref for this outer voltage loop. So, you will have current as a reference. So, ID ref as you generate from here, it will be used here, and then for this it is called current control voltage source inverter, and you will be compared with the ID, and you have a cross term that comes from the IQ and you multiply it with the omega LF and you have PI controller Vd, then you will actually subtract Vd which is here, and thus you get the VDF reference. So, this VDF reference will be fed here. Similarly, same for the VQ. So, this is the explanation of the current control voltage source inverter, and the inner current control loop allow faster dynamic response and improved TSD in the output voltage under various operating conditions. Thank you for your attention. We shall continue to our discussions in our next class. Thank you.